Hello, quantitative methods. And in this part of the lecture, we're going to talk about the null hypothesis significance testing in its entirety. Again, very, very important topic because the way that we're going to be doing inferential statistics throughout the rest of this class is looking at them through the eyes of null hypothesis significance testing. It is one way to deal with the critical problem of inferential statistics, the fact that we might have just found our mean differences just due to chance. All right, so the way that psychologists and most scientists tackle this problem, at least nowadays, is via null hypothesis significance testing. All right, so we talked about Sir Ronald Fisher's contributions with the p-values. Now we're going to talk about Neyman and Jerzy Neyman and Egon Pearson's contributions. All right, so what is null hypothesis significance testing? Well, what we're going to do is whenever we have an inferential statistics problem, we're going to create two different hypotheses. One is going to be the research hypothesis or the alternative hypothesis. And I'll use these two terms interchangeably because they're used interchangeably throughout the literature. So it's either an alternative hypothesis or a research hypothesis. And this is our prediction that there is an effect in our study. There is a mean difference between UGA and UNG students on psychology test scores. There is a difference between people that own a dog and the national average for anxiety scores. So there is a difference. That's what the alternative or research hypothesis suggests. All right. And so we have that hypothesis, and then we have the null hypothesis. The null hypothesis is the hypothesis that there is no effect, that the population means for psychology test scores are the same for both UNG and UGA students. That the dog owners and non-dog owners have exactly the same levels of anxiety. So no effect whatsoever for the null hypothesis. So we create these two. All right, and we're ultimately trying to provide evidence for the research hypothesis, for the alternative hypothesis. And the way that we're going to do this is a little bit counterintuitive. We're going to test the validity of the null hypothesis. How well does the null hypothesis account for the data? If the null hypothesis can account for the data fairly well, we are going to retain the null hypothesis and say that it is tenable that there is no population mean differences between our two conditions. However, if the null hypothesis does not fit the data, if it is very unlikely that we have obtained the results that we did in our experiment, due to the null hypothesis, if the null hypothesis were true, then we reject the null hypothesis. And this provides evidence in favor of the research hypothesis, provides evidence for the alternative hypothesis. Right? This phraseology, this way that I'm speaking about it, might seem counterintuitive. So we're talking about rejecting the null hypothesis, and if we do that, that is evidence for finding an actual effect. So it seems counterintuitive, but it does make sense given what we're doing. All right, we don't know with the research hypothesis exactly how big that mean difference is. If it's a small difference, if it's a large difference, we just trying to test, is there a difference at all? So we can't set up our expectations for what our data are going to look like just due to chance if we don't know how big that difference is. All right, but what we can do, if we know what the null hypothesis looks like, okay, we know what the data under the null hypothesis should look like, so we test if the null hypothesis fits the data because we don't exactly know what the magnitude of the difference is, if that makes any sense. Okay, so we provide evidence for the alternative hypothesis by testing the validity of the null hypothesis. All right, so in most simple instances of null hypothesis significance testing, we attempt to test whether a given sample of scores comes from a specific population distribution of scores. All right, let me give you an example of this that we'll use for a couple of slides. Are SAT scores of students from Southern high schools generally different than other SAT scores found across the country? So this is our research question. Okay, so we're trying to see if a sample of Southern high school students, all right, is it likely that their population mean, which we don't have, we have to infer about their population mean, is it similar to the population SAT scores across the entire country? Right? Simple use of inferential statistics, as simple as we can really get with inferential statistics in psychology. This high school, by the way, is Airport High School, where I went to high school in Columbia, South Carolina. You can't imagine what it was next by and why they named it, right? It's by an airport. They called it Airport High School. Very, very creative, the administrators were. All right, so this is our research question. Let's first start talking about creating our research and our null hypothesis. So first of all, research alternative hypothesis, as I mentioned before, we use these terms interchangeably. If we're going to use notation, I'm going to use H sub A to refer to the alternative hypothesis. This, of course, is the hypothesis that states that there is an effect. There are differences between our population means. Most of the time in this class, we'll be dealing with inferential statistics, looking at differences in means, but any kind of effect in inferential statistics we can look at with this. Okay, null hypothesis. We're going to abbreviate that as H sub 0. Not sub-zero like the Mortal Kombat character, but a lower 0 here. This is the hypothesis that there is no effect, maybe no differences between the population means. Okay, it is the exact opposite of the research hypothesis. In fact, these completely take up the probability space. It's either the research hypothesis is true or the null hypothesis is true. There isn't a third option. They can't both be true. It's one or it's the other. So if we're looking at our example of Southern students from Southern high schools, are their SAT scores similar to the general population? Well, our alternative hypothesis is that there's a difference. So notice how I write this alternative hypothesis. All right, H sub A, same notation that I'm using right here. And I'm referring to the population means because this is what we're inferring about. This is what we care about. Who cares about the sample means? Okay, if we grab 20 high school students from the South. All right, we don't care about that sample. We want to infer about all students from a Southern high school. So I have the mu symbol. Mu, remember, is the population parameter for the population mean. And I'm going to use these little sub notes to denote what population mean I'm talking about. So SS for here for Southern students. How do we write is different in mathematical notation? All right, if it's different, that means that it's not equal. So I'm going to use the does not equal sign. And then population mean for the national average here. That's what this means right here. All right, in other words, the population mean for SAT scores for Southern students is different from the national population mean for SAT scores. All right, this is our alternative or research hypothesis. Our null hypothesis is the exact opposite of this, all right? That the population mean for Southern students is equal to the national population mean for SAT scores. Here's a hint. Anytime that we are doing a null hypothesis, there has to be an equal sign in there somewhere. It might be a regular equal sign, it might be a greater than or equal sign, it might be a less than or equal sign, but there's got to be an equal sign somewhere in our null hypothesis, at least in this course. Okay, so our null hypothesis is that there are no differences between the population mean for Southern students and the population mean for the national average of SAT scores. All right, so as I mentioned before, the logic behind null hypothesis significance testing is a little bit counterintuitive. We do not know the magnitude of this difference. We don't know if it's the case that Southern students are smarter than the national average. We don't know if they're dumber than the national average using the SAT. We don't know the magnitude of that difference. Is it a huge difference? Is it a small difference? So we can't calculate probabilities for things that we don't know what the effect is going to be. But we do know what the data would look like under the null hypothesis. Okay, so what we're going to do is we're going to draw and examine a sampling distribution of what a sample mean would look like if the null hypothesis were true. Okay. In other words, we're going to test the likelihood our data are if the null hypothesis is true. Is there a high probability that we would obtain some data like this if the null hypothesis were true? So we draw the sampling distribution of what our data would look like if the null hypothesis were indeed true. And if it's very unlikely that we obtained a sample mean of this extreme value, it's very large, maybe it's very small, it's very unlikely that we would have drawn that mean by chance from the normal sampling distribution that we have under the null hypothesis, then we reject the null hypothesis. We say, well, there's a very low probability that we would have found this result if the null hypothesis were true, so we're going to reject the null hypothesis and provide evidence for our research hypothesis that there's a true difference between the population means. All right. Conceptually, we're going to reject the null hypothesis when it makes our sample results very unlikely that they're due to chance. So we either reject the null hypothesis or we're going to fail to reject the null hypothesis. We never accept the null hypothesis. All right, even if the data is very likely that they were to come if the null, let me back up. It's very likely that our data we would have obtained if the null hypothesis were true, like there's like a 50% chance that we'd have found the data like this. We still never accept the null hypothesis. We never do that. And if you do that, if you say in a paper or you say in a test question that we accept the null hypothesis, I'm going to throw something at you. All right, so don't do that. There's a conceptual reason why we don't do this. There might always be a difference between the population means so very small that it is unlikely that we would detect it using the statistics, using the research study that we conducted. So we never accept it, okay? We never accept the null hypothesis, at least in traditional null hypothesis significance testing. So don't use the word accept when we're talking about these things. All right. So after analyzing the data, after calculating the results, there are two options. We can either reject the null hypothesis and conclude that there is a true difference in our population means, or we can fail to reject or retain the null hypothesis. All right, fail to reject or retain, same thing, you can use either of those terms, and conclude that there's no population mean differences. All right, so if we can reject the null hypothesis in favor of the alternative, or we can retain the null hypothesis and retain the null that there are no population mean differences between our two conditions, between our sample or between the population that our sample comes from and another population, depending on the kind of test that we are looking at. One sec. All right. So we can either retain the null hypothesis or we can reject the null hypothesis. How do we end up making this decision? We need to create some decision rules. All right, we need to come up with some way in which we're going to know whether or not we should reject or retain the null hypothesis. Now, historically, the cutoff point that we decide, okay, if it's past this cutoff point, we're going to reject the null hypothesis. The cutoff point has historically been 0.05. All right, 0.05 being the probability that if we obtained a result and it's where it is either at 0.05 or lower than 0.05 probability that we would have obtained that result due to chance, then we reject the null hypothesis. However, if the probability that we obtain this result due to chance is higher than 0.05, then we retain the null hypothesis. All right, why is it 5%? Okay, why is it 0.05? Why isn't it 0.01 or 0.10? Well, one day Fisher suggested that it should be 0.05, and everybody is kind of stuck. All right, and in psychology, it's pretty much immutable. All right, you can't really deviate from that 0.05. If you're the probability that something occurs to chance, which again, remember, is our p-value. If we calculate a p-value that's above 0.05, we can't really say much about our data. Okay, we have to retain the null hypothesis. All right, so that cutoff, at least among all psychologists, among many statisticians, we've all pretty much agreed that it's 0.05, and we don't dare move it, or otherwise people get a little bit mad and say, why did you move it? Okay, maybe it's the case that you might be fudging your data a little bit to say that there's a real difference when really there's not, and that's the reason that you moved your cutoff from 0.05 to something like 0.10. All right, but I'm getting a little bit ahead of myself. All right, what is the what's that decision criterion called? All right, what is that level that if it's below this, then we reject the null hypothesis? If it's above it, we retain. Well, that rejection region is called the alpha level. All right, the alpha level is something that we set before the experiment begins, before the research study begins. All right, and as I mentioned, it pretty much is always going to be 0.05. So the alpha level, this is our decision criterion. This is what we set up beforehand. All right, so we need to make sure that we formulate our research hypotheses and null hypotheses before we begin our research study. We need to specify our decision-making criterion before we begin our data analysis. Otherwise, someone might kind of fudge the data a little bit to make it seem like they have a real effect when in actuality they might not, okay? Maybe you conduct your study and you find that your p-value is like 0.06. Well, that's close enough to 0.05. Why don't I just write my paper in such a way that says, hey, my cutoff is 0.06. All right, well, that's definitely stacking the deck in my favor. All right, and this is going to inflate some of the errors that we end up making when we do null hypothesis significance testing. And we don't want to make any errors. We want to be as truthful as possible. So good rule of thumb is that we make all of these decisions about the statistics that we're going to do before the study begins, before we start looking at the data. That's the more ethical thing to do. I'll talk a little bit about this later on and why that's a problem. So a common problem that students have is they get confused between p-values and alpha levels. So the alpha level is something that's set before we conduct our statistics. The alpha level does not change. All right, it's 0.05, it's going to be 0.05 throughout the rest of the experiment. So this is our decision criterion. All right, and if the probability that we obtain this result just due to chance is below the alpha level, we reject the null hypothesis. Otherwise, we're going to retain or fail to reject the null hypothesis. And again, these mean the same thing. Okay, how is that different than the p-value? The p-value is a calculation. It's not something that we set. We calculate the p-value after our study is over. All right, it's the probability of obtaining a result as extreme or more extreme if the null hypothesis were true. So it's the probability of obtaining a result at least as extreme as the observed results if the null hypothesis were true. What's the relationship specifically between these? Okay, now obviously they're different things. One is set. It's always 0.05 for the alpha level. The p-value always changes, and we end up calculating it for our study. But again, we typically don't do that. We get our computers to do that. Well, if the p-value is lower than the alpha level, then we reject the null hypothesis, and we say, we think that there's population mean differences here. If the p-value is greater than the alpha level, then we retain the null hypothesis. It's likely that the data that we are looking at, the data that we collected, the sample that we've got, is we found this difference just due to chance, just due to random selection error. Okay, so even when we set a cutoff at the extreme part of a sampling distribution, there's still a chance that we might make a mistake and the null hypothesis might actually be true. All right, even if we set our criterion at 0.05, that's still a 5% chance if the null hypothesis is true, that we make a mistake. That we say, hey, we really think that there's a difference, but in actuality, there is no difference. What kind of error is this? In statistics, we call this a type 1 error. All right. The type 1 error is where we reject the null hypothesis and we say, hey, I think that there's some population mean differences. These are interesting. But in actuality, the null hypothesis is true. So we're saying that there's an effect, but in actuality, there is not. Another way of describing this is kind of like a false positive. All right, think about false positives with medical tests. All right, so because the era that we're living in, let's talk about COVID. So a type 1 error would be the doctor saying, hey, I think that you have COVID, but in actuality, you do not. All right, so we want to minimize these false positives as much as possible. We don't want to tell our readers, we don't want to tell the viewers of our study that we've got a really cool effect, when in actuality, the differences that we see in our sample means are just due to chance. Okay. So in null hypothesis significance testing, we set our type 1 error rate. Our type 1 error rate is our alpha level. Okay. So our type 1 error rate is our alpha level. That's what we set. That is our decision criterion. So our type 1 error rate is never going to be above 0.05 if we are doing things correctly. If we're not doing things correctly, there might be some problems. But we need to make sure, and our goal is, for the majority of this class, that we want to get that type 1 error rate down to 0.05 or less. All right. So when the null hypothesis is true, the type 1 error rate is equal to the alpha level. If the null hypothesis is false, there can be no type 1 error. Okay? Think about that. Type 1 error only comes into play if the null hypothesis is true. If the null hypothesis is false, if there's really a difference, you can either say, I reject the null hypothesis, and then you're correct, and you have found a difference, or you say, oh, I don't think that there's any difference. And that's a different kind of error. Okay? So type 1 error only occurs when the null hypothesis is true. So what we do when we are doing null hypothesis significance testing, let's just draw what our sampling distribution is. Now remember, from module 4, when we were talking about normal distributions, we talked about sampling distributions, and we can know what a sampling distribution looks like. Remember, central limit theorem, it's going to be normally distributed if we have 30 or more subjects. All right, or if the population distribution was already normally distributed. We know what the variance of this is. Okay, we know that the standard error of the mean, we can easily calculate that. We know what the population mean of a sampling distribution is. Okay, it's just the population mean. So we know what this distribution looks like. All right, under the case that the null hypothesis is true. So what we end up deciding to do is we create a rejection region. All right, and we draw that rejection region, and we see what the value is here. And if we have a value above it, okay, we decide that we're going to reject the null hypothesis. If we have a value below it, we're going to retain the null hypothesis. The area underneath the curve for this probability distribution, remember, for probability distributions, the area underneath the curve is always 1. But we find the location in which the area underneath the curve here is 0.05. Because remember, that is our alpha level. That's where we're setting it. So we are setting a cutoff point for right here that we're going to try to calculate a statistic. And if it's above this, we're going to reject the null hypothesis. And if it's below it, we're going to retain the null hypothesis. All right. So that's right here. We talked about normal distributions and that they're asymptotic about their x-axis. They never touch the x-axis. It never goes to 0. So even if we wanted to be very conservative about our decision criterion, I can move this bar to make it more extreme. The difference would have to be even greater for me to reject the null hypothesis. There's always going to be a sliver. There's always going to be a small percentage that I am going to make a type 1 error. Okay, I can never get rid of this. I mean, I can practically get rid of it and make this cutoff very, very extreme. But if I do that, I'm very unlikely to ever reject the null hypothesis. I'd have to have a massive difference for anybody to reject the null hypothesis. And that would be problematic in and of itself. So we always have some type 1 error. Another thing that we can do, we'll talk a little bit later, is maybe it's the case that we want to have 2 rejection regions. Here, we are making a prediction that the mean difference goes in one direction, so that maybe it's the case that owners of a dog have less anxiety than the general population. But maybe we just want to see, is there a difference at all? And if we want to say if there's a difference at all, we have to set up 2 rejection regions, all right? One at the lower end of the sampling distribution and one at the higher end of the sampling distribution. And these cutoffs are going to be more extreme than the cutoff over here, because the area underneath the curve, both over here and here, has to be equal to 0.05, okay, because that's our type 1 error rate. That's the alpha level that we set. So the area underneath the curve over here is going to be half of alpha, which is going to be 0.025, and it's going to be 0.025 right here. Okay, we set these 2 cutoff rejection regions when we don't know and we don't have a guess as to what the population difference is going to be between our 2 conditions. Is it going to be higher? Is it going to be lower? Is this population mean going to be higher than this other population mean? If we don't know and we just want to see, is there any difference, we need to set up 2 rejection regions underneath the sampling distribution. All right, moving on. So type 1 error, a false positive. We say that there's an effect when in actuality there is no effect. Now, there's also another kind of error that we can make. All right, there's a chance that the alternative hypothesis is true. There is really an effect, but we fail to reject the null hypothesis and we retain it. This is known as a type 2 error. Notice how I write type 2. I don't put the numeral 2, I use the Roman numeral 2. And that's how we typically refer to these things. So type 2 error is the error that we retain or fail to reject the null hypothesis when indeed the alternative hypothesis is true. Okay, we retain the null hypothesis, but the alternative hypothesis is true. Another way of referring to this would be as a miss. There is an effect, but we missed it. All right, if we're thinking about a medical test, you really have some kind of disease, you really have some condition, but the test missed it and said that you were fine. That's what a type 2 error rate is. Now, we can't set the type 2 error rate, all right, because we don't know what the magnitude of the difference is, okay? If we knew the magnitude of the difference, we would not even have to use inferential statistics. So we can't set the type 2 error rate. We can guess what the true population mean difference is, and then from that, we can infer what the type 2 error rate is, but we'd have to have knowledge of what the true population mean difference would be. But the probability of retaining the null hypothesis when the null hypothesis is actually false is our type 2 error rate. Okay, but again, we can't set this in the same way that we set our type 1 error rate. All right, so suppose here we have what truth is. All right, we have 2 different populations. Let's just say for laughs and giggles, this is U and G here in blue and UGA in red. All right, let's just say that that's what's going on here. Okay, and we've decided, okay, we know what the population mean is for U and G, and we're just going to sample individuals from UGA. And we're going to come up with a rejection region right here, and we're going to set up one maybe on this side of the graph and maybe one on this other side of the graph, and this is going to be alpha divided by 2 because we set up 2 rejection regions. So the area underneath the curve right here is going to be 0.025. All right, so this is what UGA really looks like. All right, So if we randomly sample 30 or so students, half the time we're going to be above that cutoff. We're going to be over in this general area. Half the time we're going to be below that cutoff. Okay, so since the null hypothesis is indeed false, okay, because we know what truth is beforehand with this graph, there's a 50% chance that we're going to make a type 2 error rate, or we're going to make a type 2 error. That's a problem. All right. So that is the type 2 error. Another way of referring to the type 2 error rate, or probability of making a type 2 error, is beta. All right. Contrast beta with alpha for alpha level. Alpha is the probability that if the null hypothesis is true, that we reject it falsely. Beta is our type 2 error rate, that if the null hypothesis is indeed false, is the probability that we retain the null hypothesis. All right. So this is a chart that I want you to be familiar with. So in reality, it could be the case that we have a population mean difference, that there is an effect, or it might be the case that there is no effect. All right, and we can either say that there is an effect and reject the null hypothesis, or say that there's not an effect and retain the null hypothesis. All right, we could, there could actually be an effect, and we say that there's an effect, we reject the null hypothesis, and we get a clap. We actually find something, we get our paper published, lots of people love us, all that kind of thing. Okay, that's one outcome. Another positive outcome for us to have is maybe in reality, there is no effect, and we conduct the study and we retain the null hypothesis. This is a true negative. Now, we might not be able to, we might have predicted that there was an effect, and so this is a bit of a bummer, but anytime we get to truth and make the right decision, we should be proud of ourselves in a science. Okay, we should be proud of ourselves that that's the finding that we get. Okay, and sometimes the null hypothesis is indeed true, and that is sometimes just as important then there is mean differences. So don't be bummed out if you get have to retain the null hypothesis when you're doing your own study. It is still important. All right, so those are the good outcomes. What happens when in reality there is not an effect and we say that there is one? We're committing a type 1 error. And again, we set that type 1 error rate before the experiment, that if the null hypothesis is actually true, there's only a 5% chance that we make a type 1 error. The other kind of error that we can make is that there is truly a mean difference, population mean differences between our conditions, and we say that there is not one. All right, and this is our type 2 error. And this is what we call beta. Okay, we don't set what this is because when we start our study, we do not know the magnitude of the population mean difference. Okay, so it's never logically possible to ever prove the null hypothesis. There's always some chance that it's itty bitty difference. Okay, hypothesis testing is a probabilistic method, and we can repeat this experiment again and again and again. And we might get an extreme result and then reject the null hypothesis. So when we fail to reject the null hypothesis, we say that the null hypothesis is tenable. Just a couple of things to keep in mind here. One more thing that I want to mention here is that we might set up our rejection regions differently depending on our hypothesis. And this is something that I mentioned a little bit earlier. If we don't have a hypothesis and we want to test if the two population means, if one is greater than the other or the other's less than the other, and we don't know the direction of the difference, we set up and conduct a two-tailed test. It's two-tailed because there are two rejection regions. There's one on the left tail, there's one on the right tail. If we have a prediction, okay, and we know the direction of our effect, and we have guessed that beforehand, then we might set the rejection region only on one side of the sampling distribution. And so this will be a one-tailed test. Okay, one-tailed because the rejection region is only on one side. All right, so Maybe it's the case for a one-tailed test that we're predicting that the mean of the first group will be bigger than the mean of the second group. Another example, anxiety scores are lower for people who own a dog compared to the general population. That research hypothesis would warrant a one-tailed test. Or maybe the case that population mean psychology test scores are higher for U and G compared to UGA. All right. Again, if we have a prediction, then we're going to put the rejection region only on one side of the sampling distribution. So what that's going to do is it's going to increase the likelihood that we reject the null hypothesis. So it's going to decrease our type 2 error rate from switching to a two-tailed test to a one-tailed test. And that's a good thing. But the problem is that let's say that we are predicting, let's say for this dog examples, that anxiety scores are lower for people who want a dog. But it turns out that they're actually higher, all right? And in fact, they're much higher. At that point in time, can we reject the null hypothesis and say, hey, there's a population mean difference? No, we can't. That's unethical for us to do that, okay? Because we set the rejection region on the other side of the sampling distribution. All right, if we were to reject the null hypothesis under that circumstance, well, then we have inflated our type 1 error rate. Okay, and again, we're trying to make sure that our type 1 error rate is 0.05 or smaller. All right, so we might miss out on a result if the result is in the opposite direction if we conduct a one-tailed test. So we need to be mindful. Just some examples of what these sampling distributions are going to look like. Here we have a sampling distribution, which we have two rejection regions. Okay, one rejection region on the left side, another on the right side. Again, these rejection regions should add up to 0.05. So if we were to calculate the area underneath the curve right here, it would be 0.025. Over here, it would be 0.025, so they'd add up to 0.05. Here is a sampling distribution in which we have a single rejection region. And so this is a one-tailed test, okay? The rejection region is only on one side of the sampling distribution. All right, so we don't want to make errors. We want to get at truth. How do we get at truth? Well, how do we decrease the probability of making a type 1 error? Okay, what we can do is we can decrease alpha. Instead of alpha being 0.05, we make alpha 0.01. So there's only a 1% chance that we reject the null hypothesis when the null hypothesis is false. All right, that's good. And we could do that, but the problem is our type 2 error rate would increase. So we don't want to do that, okay? Only if we are trying to be very, very conservative. And there's some disciplines that do this. So for instance, if you're in physics or if you're in engineering and you're doing some statistics and you want to be very certain if you find a particular effect, you might decrease the type 1 error rate by changing what alpha is to make it much smaller. But typically you don't see this happen very frequently in psychology. All right, how do we decrease the probability of making a type 2 error? Well, there's a couple of things that we can do. We could increase our cutoff for alpha. So instead of alpha being 0.05, we change it to 0.10. All right, but the problem with that is, yes, it is going to decrease the type 2 error rate, but it's also going to increase the likelihood that we make a type 1 error rate, or that we make a type 1 error. And so people don't do this. All right, this is cheating, kind of fudging your data a little bit. It's frowned upon. So we typically do not see this. This is not feasible. You would not get a study published doing this. Things that you could do, you could switch from a two-tailed to a one-tailed test. All right, this is going to decrease the likelihood that you commit a type 2 error. But again, you want to have that prediction and that hypothesis beforehand. If you don't do that and the data is in the opposite way of what you predicted, you could not reject the null hypothesis and say that there's truly a difference. So you need to be mindful of that when you switch from a two-tailed to a one-tailed test. Can you look at the data and then decide if you want to do a two-tailed test or a one-tailed test? No, that's cheating. All right, you have to make the decision to make a two-tailed or to use a two-tailed test or a one-tailed test before beginning the study. All right, because might be the case that the mean difference that you have is only significant if for the one-tailed test you only reject the null hypothesis under the one-tailed test, but not the two-tailed test. Okay, the two-tailed test is more conservative, And if you do that, of course you do the one-tailed test, but that's unethical. Can't do that. The easiest thing that you can do is to increase the number of subjects that you have. All right. If you increase the number of subjects that you have, this is going to increase or decrease the likelihood of you committing a type 2 error. Think about what happens to the standard error of the mean when we increase n. The standard error of the mean is the population standard deviation divided by the square root of n. The standard error of the mean is going to go down as the number of subjects goes up. All right, that means that the sampling distributions are going to get skinnier and skinnier and skinnier, and it's going to be easier and easier and easier to tell if a difference is due to a true difference compared to chance if those sampling distributions are skinnier. Okay, we are better at estimating what population means are if we have a large number of subjects, no doubt. So increasing the number of subjects that we have will decrease the probability of committing a type 2 error. And the last thing that you can do is strengthen the manipulation. So maybe if we're looking at the influence of naps on memory, so maybe instead of taking a 15-minute nap, you take an hour-long nap. This is going to maybe increase the population mean differences between the nap and the no nap condition. If you think that Prozac decreases depression, well, instead of taking it for a week, you have people take it for 4 weeks. That's, again, likely to create a greater difference. We think people that own a dog, it decreases their anxiety. Well, let's get dog owners that have owned a dog for a long period of time compared to people that have owned the dog only for a week. All right. If we strengthen our experimental manipulation or strengthen whatever the conditions are, we're more likely to find a difference. So that's one thing that we can do if we're trying to reject the null hypothesis as well. A lot of this lecture is very conceptual and it will be hard to understand. We're going to go to the next module with one sample z-test, and there it will make some more sense what exactly we're doing with all of this language. So don't be too concerned if you don't completely understand what's going on right now. But I would suggest that you rewatch this video a few different times throughout this course because some of these concepts are very, very important. All right. Good luck studying everything, and I hope you all have a wonderful day. Bye-bye.